Today, we're going to explore the cosmological redshift. Cosmological redshift. This is the picture you should keep in mind as we're discussing this. So we are here. Let's say here's a galaxy, and you are here. And some distance away, there's another galaxy. And at some time, TE, there's a photon that's emitted. It travels along and it arrives here at some later time. We'll call that TR. And then sometime later, there's another photon that's emitted at TE plus DT sub E. So this is a second photon that's emitted just a little bit later, and it travels through the universe, and all the while these photons are traveling through the universe is expanding. There's a characteristic scale for the universe that is growing with time. That characteristic scale is A of t. And when the second photon arrives to us, it arrives at TR plus DTR. The cosmological redshift relates the interval of time at emission to the interval of time when it is received. Those are not necessarily the same. So since we're discussing the travel of photons through the universe as it's expanding, we need to consider the light-like interval. So the interval for the Robinson-Walker metric is ds squared is equal to minus c squared dt squared plus a squared times dr squared plus L squared d omega squared, and L of R, L is a function of R. For some reason that didn't. There we go. L of R is equal to R if k equals 0, or in other words, flat space. Sine of R for k equals +1, positively curved or spherical space, or hyperbolic sine of R if k is equal to -1, hyperbolic space. And d omega squared is equal to d theta squared plus sine squared theta d phi squared, the angular portion. Okay, so we have the interval, and a light-like interval is one in which this interval is equal to 0. So if this is equal to 0 and we only consider motions in the radial direction, so d omega squared is equal to 0, then we're left with the expression that c squared dt squared is equal to a squared dr squared. And then taking the square root of this, we have that c dt is equal to plus or minus a dr. And the sign The plus sign would be as time increments forward, we're considering incrementing dr in the positive direction, and the minus sign would be as time increments forward, we're considering dr going in the negative direction, negative r direction. Since we are considering photons leaving some source and coming towards us, and we are at the center of our coordinate system, then we're going to choose the minus sign. So we have that c dt is equal to minus a dr. And a is a function of t, so we can move that to the left-hand side. And so now we have the integral of the left-hand side, so c integrating from t emitted to tr dt over a of t is equal to minus the integral from the starting position at t emission, which is at some coordinate r, and then the final position is 0 of dr. We have the minus sign, and this equals r. Remember, this r is a co-moving coordinate. Which is independent of time. All right, we're going to use that fact in a moment. All right, so let's draw what the situation looks like graphically. We're going to draw the integrand of the left-hand side, so 1 over at, and put all of this in context. So this is time, and then our function is 1 over a of t. Since a of t represents the scale of the universe, and for this hypothetical situation, we're talking about a universe that's expanding. So 1 over a of t will go down with time. So this 1 over a of t goes down with time, something like this. And we're doing an integral of this curve. And let's say this is t sub e, and then sometime later, so this represents over here, this represents the 1 over the scale of the universe when the photon was emitted, and this over here represents 1 over the scale of the universe when the photon is received. And so this is TR. And then sometime later, at TE plus DTE, a photon is emitted. And then sometime later over here, this is TR plus DTR, the photon is received by us. I'm just going to extend out, let me extend out the axis over here. Okay. And if you recall, the integral between t and tr, or the area under this curve, so the integral in this region here, the area here, corresponds to r. We're going to use this diagram to relate dTE to dTR. And you see that we have an area here. We have moments marked by when the photon is emitted and when it is received, both a little bit after the first emission and a little bit after the first received photon. So just to recall, initially we have events TE, R are connected by a light-like interval to TR, 0. And we also have the event TE plus DTE, R is connected by a light-like interval to the event TR plus DTR, 0. Let's consider the second photon when it's emitted and then when it's received. So the second photon, it leaves at TE plus DT sub E, and it's received at TR plus DTR. And we're going to integrate DT over A of T. This is going to equal, in the same way up here, this part here, this integral here, it's going to equal that interval again. So this equals R again. In other words, we have that the integral of these two between these two intervals are equal to one another. All right, now what we're going to do is we're going to take this left-hand side and we're going to break it apart into components and one of the components is going to be what we see on the right-hand side here. So if we look at our graph up above here, we have that from here to there, that's the integral from TE to TR. And then let's use a different color. We use this color. From there to there represents the integral on the left-hand side. So to get to the integral on the left-hand side, we see that we can take the initial integral and we can add the part that goes from here to there. So TR plus integrate from TR to TR plus DT. So if we add that to the original integral, and then if we subtract out this integral that goes from TE to T plus DTE, we get back the original integral. So in other words, this left-hand side equals, let's change this back to that color. The left-hand side equals C integral from TE to TR dt over A plus, we're going to add that part that's on the right-hand side, TR to TR plus DTR, dt over A. And then we subtract off the little bit of portion on the left-hand side, TE plus TE DTE of dt over A. And this equals the right-hand side, which is C integral from TE to TR dt over A. All right, so why did we do that? Well, I noticed that the term on the far right-hand side and the far left-hand side, those cancel. And we're left with the expression that the integral from TR to TR plus DTR dt over A of t is equal to the integral TE plus DTE dt over A of t. And in the limit that these dt's are small, these approximate to dt r, so the dt evaluated when it's received divided by A of tr is equal to dt emitted over A of t emitted. And so now we have a relationship between the interval in time, dte, and dtr, between when it's emitted and when it's received. And just remind you that the frequency when it's received is defined as 1 over dtr. And the frequency when it was emitted is equal to 1 over dte. And so plugging this in, we have that the frequency of the signal when it's received divided by the frequency of the signal when it's emitted is equal to the scale, the ratio of the scales of the universe when it was emitted over the scale of the universe when it's received. Or since C is equal to lambda times nu, we have that the wavelength when it's received divided by the wavelength when it was emitted is equal to the ratio of the scales of when it's received to the ratio of the scales when it's emitted. And we see that from this, if we consider the size scale of the universe as some variable, right? So we fix the size scale of the universe when the photon is emitted, and then we consider the size of the universe sometime later, i.e. t sub r, then we find that the frequency of this signal, i.e. the photon, scales as 1 over the scale of the universe, and we find that the wavelength is proportional to the scale of the universe. All right, so that is cosmological redshift. All right, so let's go ahead and define what we mean by redshift. So redshift implies a shift to the red. All right, so a change in the wavelength. So we're going to define the change in the wavelength, delta lambda over lambda emitted. Well, delta lambda is equal to lambda r minus lambda emitted divided by lambda emitted, which is equal to lambda r divided by lambda emitted minus 1, which is equal to, now I'm going to use the result we just derived for the cosmological redshift, A of TR divided by A of TE minus 1. And if we just normalize the scale of the universe, today, so the scale of the universe today, so received, is equal to 1, then 1 over A of t minus 1 is equal to z. And note that this A of t, this t, is defined to be the scale of the universe when the photon was emitted. Sometimes there's some confusion on which A of t we're referencing, but hopefully that clears it up. Or if we solve for A of t, then A of t is equal to 1 over 1 plus z. So if you take the spectrum of some galaxy and you notice that the lines are redshifted, so redshift would be measuring delta lambda over lambda, and it would be positive in that sense, then you can plug in that measurement of the redshift, delta lambda over lambda, into this expression, and it gives you an expression for the size scale of the universe at that time compared to what it is now.